Today we're going to be doing a k-means clustering analysis on Japanese vowels using the formants and the bandwidths of the vowels. This data set, it is unlabeled, which means that we don't know the identity of those vowels. We're going to use k-means clustering to try and create groups, and then it'll become pretty straightforward which vowels are which. First, we should talk about k-means clustering, what it is, what it isn't. Probably easiest to discuss k-means clustering in reference to something you're probably already familiar with, which is simple linear regression. In simple linear regression, we take two variables. Let's call these height and weight. And let's say we took 30 students and we got them to self-report their height and weight. You might have a couple of outliers, extremely tall, light individuals, heavier, shorter individuals, but generally what we're looking at is a positive correlation between these two variables, where people who are taller are typically heavier than those that are shorter. Now, the way that we fit this regression line is by determining least square, which is what we do is we take a measurement of where each of these samples sit, and we calculate what the distance is across both planes, and that's the square. We're trying to get that least square, the combined least square of all of these samples, to be as small as possible, right? Okay, so that's how it works in linear regression. What does it mean to be least square in k-means clustering? Okay, well, in linear regression, we're testing a hypothesis that variable x has some kind of effect on variable y. In k-means clustering, we're not testing that kind of hypothesis. What we're doing is we're testing the kind of hypothesis that says something along the lines of, there are these distinct groups, and I can prove mathematically that they are distinct from each other. So let's say that we have vowels. Here we have Formant 1, and here we have Formant 2, and Professor Smith of Smith University has determined that there are 5 vowels in this system. And you've taken a look at these Formant values and you said to yourself, well, that doesn't look like 5 vowels to me, that looks like 3 vowels. And I can prove that mathematically using k-means clustering. In k-means clustering, what happens is we draw a line around these samples in order to determine what is least square for each individual cluster. So each of these clusters has a mean, a midpoint, and what we're trying to do is reduce that value, how the distance of each sample is to that mean, right? Now, in this data set, let's pretend we have 30 samples. And we're thinking about least square. K stands for the number of clusters that you're going to be using in your analysis. Now, if n equals 30 and k also equals 30, so if k equals n, then that's the least square, right? Because what's going to happen is each sample is going to be its own individual cluster, and its mean is going to be its value. So therefore, there is no distance from the mean, right? However, 30 clusters for 30 samples, it serves no purpose. There's no value to that model. And what we're trying to do is we're trying to build a valuable model that says something about the world. So how do we determine the value of k? There are a few ways to determine the value of k. The one that I'm going to talk about right now is probably my least favorite, but it's my easiest to explain visually. We will talk about the other ways of determining the value of k. All of the methods I use to determine the value of k aren't very useful in this data set, but we'll talk about why that might be at a later time. Anyway, let's say that k equals 1. We'll call this can be square, And this is number of clusters, or okay. And we have 1, 2, 3, 4, 5. Now, let's say that dealing with that previous data set, we use one cluster. Well, okay, well, square is at its maximum in that instance, right? You've drawn a big circle around every single sample. You have your mean in there, but the square is at its maximum point because every sample is trying to fit to this one cluster. However, then we introduce a second cluster, and what happens? We see a great big drop in square, right? So what's happened is we've introduced this second cluster, and now we have two groups, two different mean points, and each of those samples is trying to fit to those mean points. So we're going to see a big reduction. And then we probably see another reasonable reduction once we introduce that third point based on that previous data set. But then what happens is we start to see this plateau. Okay. Now, this here is what we call the elbow method for determining the number of clusters. The elbow method is essentially what you're doing is you're eyeballing to where the elbow joint is or to where that plateau begins. And you're going back one and you're saying, okay, well then K equals 3. Okay, now as you increase the number of K, you're going to see a decrease in your square, right? Because you're increasing all of these new mean points. And so you're decreasing that value. But the usefulness of increasing K will plateau at some point, right? And for that previous data set, we had 3 fairly distinct vowel clusters using the first 2 formants. So it makes sense that that plateau would begin at about 3 clusters. Okay, so that's how we determine the value of K. Now what we're going to do is we're going to take a look at the data. We're going to start building some of these models. We're going to see how useful they are for clustering vowels, or at least clustering Japanese vowels. So let me share my screen so we can move on to the next part. Okay, I'm sorry, I've done this. This isn't my normal computer. I apologize about the microphone quality as well. I've just had to reinstall. I've just had to do a fresh install. So at some point, there might be some gremlins in the system. But let's talk about this code. For this code, which I will post a link to in the description, we're going to be using the stats package, the dplayer package, ggplot2, ggfortify, and factor extra. We're also going to be using this function here, the WSS plot. Now, I'm not sure exactly who to attribute this function to because I have come across it on a couple of different websites and it's not clear who wrote it first. So my apologies if this is your code. But yeah. Now the data is going to come from a URL. So let's go to that URL and take a look at what we're dealing with. Here we have a corpus of Japanese vowel formant patterns by Mokutari and Tanaka, and we can take a look at our data. And what we have is 8 columns of 2,750 samples. Okay, we don't know anything about them at this stage, right? We can take a pretty good guess. That looks like F1 and F2, which means that these are probably F3 and F4. But these ones are a little bit more difficult to identify if you haven't dealt with bandwidths before. If we go back to the documentation, we see here that Mokutari and Tanaka have very kindly said the 8 columns are structured as follows: F1, F2, F3, F4, where F1 through F4 are the first 4 formant frequencies and B1 through B4 are the bandwidths respectively. Okay, so while we don't know the identity of the vowels, we do know what these columns represent. Now, not knowing the identity of the vowels makes this data set perfect for unsupervised machine learning. Unsupervised means you don't know the classification. So the machine isn't going to be able to use that classification to learn how to do its job. It's going to have to use other information. And in this data set, that other information are the 4 frequencies and the 4 bandwidths. So let's bring in this data. Just take a look at it down here. We see each column is labeled V1 through V8, but we know that the first 4 are the Fs and the second 4 are the Bs. And because we know that V1 and V2 are F1 and F2, we can create a plot and take a look at what this data set looks like. So to me, this looks pretty clearly like 5 different clusters based on F1 and F2. This cluster here has a low F1 and a high F2, which tells me that it's probably the high front vowel. Here we have probably what is the E, the U, the O, and the A. In Japanese, we would call this A, I, U, E, O. Now, just because us eyeballing this tells us that it looks like there are 5 clusters here, we probably shouldn't base our analysis on a judgment call like it looks like, although that's exactly what we do in using the elbow method. Okay, so here we see the reduction in WSS, which is like, think of that as the square from like the distance from the mean. We see a big drop off as there's 2 clusters. It drops off a bit further at 4. 5, which is here, is where we would expect to see a plateau based on our knowledge, our existing knowledge, that Japanese has a 5 vowel inventory. However, to me, there is nothing particularly informative about this, the difference between this and this, to tell me that the number should be 5. And this is one of the big problems with the elbow method, is that it relies on kind of an arbitrary judgment by the user to go, oh, well, this is where it plateaus, so this is where I should start. This is the number of clusters I should use. Now, this WSS plot uses the plot function that's here. These methods, WSS, silhouette, and gapstat, these come from the Factoro Extra package. And here we can see this is basically going to give us the same chart because it's the exact same method as the WSS plot function. So here we see at 5 clusters, it's not really clear that 5 is the number of clusters we should be using. In fact, it's pretty ambiguous in my from my point of view. Here we use the silhouette method, which is suggesting 2 clusters, and the gapstat method, which is going to suggest an even more outlandish number of clusters. This one is a little bit more computationally intensive, so you'll have to wait for it to do its thing. I should note, I'm posting these videos on like my private YouTube account, and it occurred to me that I've uploaded videos of me and my children in that account, and I was thinking, oh, that's embarrassing because it sucks to hear your own voice. And then I thought, well, that's stupid because right now I'm speaking, and if I was, like, to me, it sounds perfectly normal, but if I was just listening to this video, I would start to cringe. But yeah, anyway, it's no big deal, I suppose, to have my videos of my children. All right, beautiful. That has finished, and it tells us that it's suggesting 10 clusters. All right, now, something we need to remember here is that this is based on the entirety of the data set, whereas this plot here was based on just F1 and F2. So it might not be that surprising that we're getting a lot of variability in terms of how many clusters this is suggesting. But because we know that Japanese has a 5-vowel inventory, we can start to run our analysis using, like, by telling the computer, hey, I think there are 5 clusters here. Do you mind taking a look at it? So we're using this k-means function. This is our data, and then 5, because that's the number of vowels we believe there to be. We're going to auto-plot that. What this auto-plot function does is it's going to give you an idea as to how well the model is doing based on whether there's overlap among these clusters. And here, there is really clear overlap. So it's telling us, well, maybe our hypothesis is wrong. Maybe the model's not functioning the way that we expect it to. You and I, we know that vowel formants are useful in identifying vowels. So there's probably something else going on here. We can take a look at the centers of those clusters. So this is the centers for all 8 of the features here. And they might give us an idea as to why things aren't really going according to plan. So if we take a look at the centers here for, this is B4, B3, B2, B1 doesn't look so bad, right? Like there's a bit of variability here, but B2, B3, B4, they don't look to be particularly useful. We know that F1 and F2 are pretty good, right? And I'm just eyeballing here to see whether there is enough variability in these means to determine whether they're kind of useful or not. F3 doesn't look too bad. F4, not terrible. But the reason why we're probably getting a bit of overlap here is because a number of these features aren't particularly useful in the model, and they're kind of confusing things. So let's do that again. But what we're going to do is kind of specify the hyperparameters for the model using the iter max and the end start. These are the default values. I've just left them in so that, I don't know, I've just left them in probably because that's what the documentation says. But here what I'm doing is I am creating an object where I am mutating the cluster, so how the model is classifying each sample. And then I'm going to ggplot using F1 and F2, but as factor cluster. So this is going to give me a scatter plot, which is going to position them according to F1 and F2, but it's going to color code them according to how the model is clustering them. So we see here with the a vowel, we're getting essentially 2 different samples in this cluster, which is telling us, well, something, you know, that shouldn't be happening. Similar here, this is our o vowel. This is u, and it doesn't look too bad, but there's bits of blue in here and red here and purple. I, our high front vowel, there's a little bit of scattered in there. And then this is and it's not really clear. This is probably one particular speaker. I can't remember how many speakers in this data set actually, but it might be one kind of outlier speaker who just produces their es or their is in a funny way. But we can take a look at that. Anyway, the takeaway story of this plot is that it looks pretty bad, right? It doesn't look like a particularly useful model has been built. So what we might do is create a new data frame that consists purely of F1 and F2, right? Because we know that those features are going to be pretty useful in this model. I should have just done this, which will show us the first 6 samples. So we're going to rebuild those k-means, take a look at the auto plot. Remember that this plot tells us how well the model is functioning by looking at the overlap between clusters. And although there is a very tight corridor here, there doesn't seem to be any overlap in these clusters. And we can take a look at the k-means for these. Now we might go back and take a look at how well, we're just going to run the same, it's just the same code using the updated data set. But what it shows us is that the model is functioning a lot better. Probably not perfect though, right? Our as are 100%. This looks like a 100% accuracy for that particular vowel, right? Our is, maybe this is right. Like this might be correct. Probably not though. Right, because these samples here, they seem to be part of this cluster, and this grouping of samples here might be part of this cluster, might be part of that cluster. If you were to introduce a new cluster into this model, I would predict that that cluster would encapsulate these samples here. But maybe not. Maybe there's something down here going on down here. And the reason why we can make a hypothesis like that is because there seems to be some confusion in the model for these samples. This should be O, this should be U. These are probably U's, but they're being classified as, well, they're being put in the same cluster as O. We don't know. At this stage, really, we don't know what's what. All right. So it turns out that I have lied to you. This is the twist in this tutorial. I've told you a terrible lie. That lie being that we do actually know the vowel identities. They're just not in the data set. If we take a look more at the documentation here, it tells us that the structure of the 2,750 rows is represented by the following nested loops. We have speakers, vowels, words, frames, which means that there'll be 5 frames of 22 of the same vowel, and then the speakers. So our first, what's that, 110. So what that means is that you'll get a 110 of one vowel, followed by 110 of another vowel, 110 of vowel 3, 110 vowel 4, 110 vowel 5, and then the speaker will change. So each 550 samples, the speaker changes, each 110 samples, the vowel changes. So using that information, we can create a new column of information with the actual vowel identity, and then use that new information to see how well our clustering is working. So let's do that now. And we might just take a look at that. Okay. So here we see our F1 and F2, and now we have this new column called vowel, and we know that every 110 samples, that's going to change value. If we use our, maybe it's this plot. So this is using now, so here in this plot, we even have the vowel identity, and the elbow, while it's clearer, it's still, I don't know. I don't like the elbow method. Let's move on. So let's rebuild the model. However, what we're going to do is we are going to, because now that we have the information, now that we have the vowel identity, what we can do is we can compare this graph, which is the k-means clustering, which is being conducted purely on, it's been conducted purely on F1 and F2, and we can have a look at the identity of the vowels according to Mokhtari and Tanaka, who have classified these vowels as such, right? So this looks much clearer, right? Like, you need to understand one of the fundamental downsides of an unsupervised machine learning algorithm is that it doesn't know anything except, you know, the information that you're giving it. It's to have a model that's this accurate is not too bad for k-means clustering, right? You can't, yeah, I don't know. This model isn't perfect. I'm sure that there are ways that we can improve it. I think I'm going to do another one of these videos. And in that video, what I'm going to do is I'm going to calculate the accuracy of, I'll calculate the accuracy of the model by determining whether the vowel identity and the clustering match up. Obviously, this is probably a 3 according to this clustering, right? It's just that there's a difference between how the number that I've ascribed them and the number that the computer's ascribed for them. But we can certainly take a look at the accuracy of the model. What else do I want to do? I want to do something fun. Yeah, all right. In the next model, what we'll do is we will build a supervised machine learning algorithm. Now that we know the identity of those vowels, according to Mokhtar and Tanaka, what we can do with that information is we can create a supervised machine learning model, extract the feature importance. So the feature importance of we'll do an XGBoost model. We'll take the feature importance of the XGBoost model and use that to determine whether other features are useful in classifying samples. Okay. All right, so the takeaways for this video. K-means clustering is a way of clustering samples into distinct groups that do not have a label. So you do not know the identity of that, or you don't know which samples should go together, such as in the case with our original data set where it was unlabeled vowel data, Formant frequencies and bandwidth frequencies. The model using all of the information wasn't particularly useful. Like it wasn't terrible, but it certainly wasn't as good as when we reduced that information. So when we limited the model to just F1 and F2, we were able to make it much more accurate. That accuracy is based on an eyeball guess. We can calculate the accuracy, which is something that I will figure out how to do and we'll talk about in the next video. And in that next video, what we'll also do is we'll construct some machine learning algorithms to see if there are other features, if there's other data in this data set that might be useful for k-means clustering. And then we will build another k-means model in order to test out that hypothesis. Cool. All right, take care.